First, I want to thank Jess, because one thing that you should do when you're organizing a conference is to give somebody a data analysis task, which is really, really important to the conference. It involves web scraping and telling everybody who the winner is. That wasn't stressful at all. But no, seriously, it was fine. Yeah, so before I get started, I wanted to bring, it's hard to follow Mara because, she's outgoing and I'm nerdy. But I didn't want to get serious too much at first, but there was something really important that came up yesterday and it has to be addressed. So we were talking about snakes and it came up in two of the talks. And so, no one's saying I don't know what to name the snake, right? And so I have some expertise here that we just got a ball python. And my son decided to name it Doodle Ramen Noodle. So I like to think that we're really good at naming animals. So if you need another long name for a pet, let me know and we'll hook you up. Anyway, he did make the party hat. So yeah. All right, so what are we here to talk about, or what am I here to talk about? We're here to talk about modeling and resampling, which should be no surprise to anybody since it's me. So what I want to talk about is how do you measure performance between models. I do a lot of predictive modeling, like machine learning stuff, and that's usually where I focus. But the stuff that I'm talking about here is really, really represented. You could use this on anything. I have examples on the website for basic survival models and things like that. But I want to talk about a way to use, kind of an odd way to use Bayesian analysis to take different models and say in practical ways which one's better or how different they are. So it's a way to quantify model performance. Okay? So a lot of times, we get this data set and we build some models, maybe we build 3 models, and at the end of the day we want to say, oh, this one is better than that one. So we compute some sort of measure of performance, like the accuracy or the area under the RC curve. Or maybe if you're doing linear regression, you'll do R squared or something like that. And so we usually have if you follow the machine learning approach, a good idea is to take your data set and split it off into a training set, which you build your model on, and a test set, which you wait till the very end to evaluate your model performance on. So 2 different sets of data. And and the question is, when I have a test set and I calculate the R squared, you might want some sort of measure of uncertainty on that. So let's say you get an R squared from one model and it's 0.9, and another model it's 0.91. Okay, that's a percentage point higher. Is that a big deal? Is that better? Should I? Because it might be that the one with the lower R squared is a model you like more for various reasons. Maybe it's really fast or something like that. So a lot of times what we want to do is we want to put estimates of uncertainty on this, a confidence interval or something like that, on the R squared, so that we can say, yeah, these 2 things are really different or they're not. But the problem is you have one data set, and for the most part, unless you're going to do some bootstrapping and things like that, it's really hard to put estimates of noise on these things. And then compounded with that is the traditional frequentist or non-Bayesian approach to doing this would be to put a confidence interval on these numbers. And I just want to remind everybody what a confidence interval actually is, which is basically, if I were to have repeated this experiment in some alternate reality 1,000 times, a 90% confidence interval, you would say 90% of those times the value would fall between these 2 numbers. So try telling that to a scientist or somebody. They're like, what? What are you talking about? And that's not really what we care about. What they typically interpret that as is something like saying, well, there's a 90% probability that the true R squared is between these 2 values. And those are 2 very different things. But luckily, Bayesian analysis, incredible intervals and things like that will give you the latter, more simple interpretation, where you get an interval and it's really the probability, a certain degree of probability that the true value is between 2 numbers based on your assumptions. And so that's, I'm not full-scale Bayesian yet, but I'm getting there. I feel there's some things I still couldn't do with that, and I was really hoping this talk wasn't following Gelman, or even worse, before Gelman. So yeah, so I want to use some Bayesian analysis to do that, and so let's see how that goes. But before we get there, we got to talk about data a little bit. So a lot of time we can resample data sets. So if you've ever heard of cross-validation or the bootstrap, what people will do is they'll take a training set, their data, and they'll do this resampling procedures that basically they're kind of like simulation procedures. They, with some methodology, leave out a somewhat random proportion of the data and you build a model on that. And the data that you didn't use to build the model is what you predict on and get your measures of performance, your summary statistics. And then you put them all back in the pot and you do another resample and so on. So you're basically taking simulated subsets of your data that you build your model on, and then you predict on the other set that was left out. And at the end of the day, if you do, let's say, 10 iterations of resampling, you get 10 R squareds. And it turns out that the average of those usually is a good measure of future performance. Okay, so that's what all resampling is. It's a way usually to get measures of performance on the data set before you get to your test set. Okay, which is computationally can be kind of a lot sometimes, but it's extremely helpful. And so this is just a little schematic of like how we use our data. We get, somebody brings us a CSV file, or like a few minutes ago, somebody says, please scrape these 2 websites to tell me what's going on. So you get all your data, and typically people separate it into a training set and a test set. And then resampling happens on the training set. And so you can see, you probably wouldn't do 3 resamples, that's not very much, but that's what I could fit on this page. And so like on the first resample there on the left, now I sort of tried to invent some terminology like last year, because people talk about the training and test set in resampling, and then it gets confused with the original training and test set. So what I've decided to do is to call these things that happen in resampling the analysis set, which is what you build your model on, is like the resampled version of your training set. And the assessment set is like your resampled version of the test set. Okay, so on the first resample, you take a little bit of data, you build a model, that's the analysis set, and then you predict what's in the assessment set. And you put it back in, and then the next resample has maybe a similar or maybe mutually exclusive set of data that's in the analysis set, and so on. Okay? So the different types of cross-validation, or the different types of resampling and cross-validation to Bootstrap, they mainly differ in how those resamples are created. Okay? So what happens is, let's say you're going to build a bunch of models. Let's say you're doing regression, you're going to build 4 models. So what people would typically do is they would take those 4 models and they would fit them each time on each one of these resamples. And so then, for this first analysis set on the left, you'd fit your 4 different models and you get 4 different predictions on the assessment set, which would result in like 4 different R-squareds. And so that's what happens when you do resampling, is the first iteration of resampling, you get these 4 estimates of R-squared. The second estimate, you get 4 different estimates of R-squared that are all based on the assessment set, and so on. So you go sort of round robin, and again, your overall estimate of performance for the first model would be the average of those R-squareds across all the resamples, okay? So here's the thing is, like, if you don't do resampling and you want to build some sort of probabilistic statement about like, hey, my performance on this model is 90% R-squared plus or minus something, you kind of need replicates, right? Has anybody ever come to you with a data set and they're like, could you analyze this? And it's like one number. I mean, that's kind of where we're at if we don't do resampling. So what we'll do is we'll use resampling, which we might be doing anyway, to tune models as a way to get replicates of this thing we're trying to measure and get uncertainty for. And that's how this happens. And so what we end up with is sort of like a 2-way layout, basically. So this is, I have code, I'll post all the code in all this. This is the Ames housing data set. Has anybody ever heard of that? I'm hoping like in 5 years it'll be the next Iris set or the next empty cars, because I'm so tired of those. But it's a data set that was from like 2013 that this guy basically scraped the website of the Iowa assessor's office. And then was used in a Kaggle competition. And so we put an R package together for it. And basically, we're trying to predict sale prices of houses. And I'm not going to go into the models or what I did or what I didn't do. But what you would do in this resampling process is I use 10-fold cross-validation, which means we have 10 separate resamples instead of 3 like I showed on the last page. And what you'll see is there are rows for each one of these resamples. So this is using the R sample package. So fold 1 is the first resample, fold 2 is the second. And then I fit a bag tree, random forest, and a multivariate adaptive regression spline model to these data. So in the first fold, these are the R-squareds that we calculated for the assessment set the first time around. The second resample, here are the assessment set R-squareds, and so on. So we have like a full data matrix. And so if you think about this as kind of your source data at this point, like if somebody brought you an Anova model, like it would look like this. The only real difference is the data, the things that we've measured that we want to analyze now is not the original sale price data, it's the actual R-squareds, which are what are in this table, okay? So now we're going to analyze the summary statistics of our models as if they were our original data, or at least data that we want to get performance measures on and contrast against different models. So we can treat this like an Anova model. The complication here is that there's usually a bunch of what we call resample to resample effect. Is you might have one resample that all the models have trouble with. So it's almost uniformly low performance. And then you might have another model that was really easy on. And then you have a bunch of things in between. So my observation is it's kind of like a mixed model, or like if you had longitudinal data, that the data within a resample is more likely to be correlated with each other than data between resamples. And so and actually you can calculate this from like a mixed model or like the Bayesian model I'll do in a minute. And the within resample correlation is 0.52, which is pretty, not zero, most likely. And, and what you can see is in this graph on the next page, these are the same data. And what I did is each line is a resample, and then you have the bagged model, the Mars model, and random forest. And you can see that, surprisingly, like bagging didn't do all that well, considering it's very similar to random forest. But the thing to notice about this in terms of the correlation structure is that, let's call this mauve, maybe? Yeah? Okay. Mauve, that resample was really, really easy for everybody. And then you have some down here, like this teal, cyan maybe, that one that was relatively low for everybody. And so the lines are not always parallel. These are roughly parallel. There's some of these resamples that are not like rank ordered the same way. But you can see there is probably a correlation structure there that we need to account for in the data, like we would with a compared t-test. Okay, so any analysis of these R-squared values ought to account for that. And so we'll do that as we go along. So here's the mathy part, and I don't think it's too bad. That if we were just thinking about like an Anova model, the typical way you would write that down is you have some like outcome you want to model as a function of some indicator variables, like are you in group 1 or group 2 or group 3. And so the math is on the left-hand side we have the R-squared, which is like our data now. And then we have an intercept, and then we have M1 and M2, which would be indicators for our models, like binary indicators. So M1 might be an indicator for the Mars model, and M2 might be the 0-1 indicator for random forest. And this is basically what an Anova model is. It's like a regression on indicator variables. Now, I haven't really talked about, the resamplers. There's no like subscripts or I or anything like that. So the way you can think about this is what we call a random intercept model. Is we're going to say like at the resample level, for a specific resample like R-squared sub I, that they have some random intercept that puts them somewhere on that curve, and then a systematic effect due to like model 1 and model 2. Okay, so what we're going to do is do what we call in like, if anybody's like a linear mixed model person, like a random intercept model, this is a really common like way to account for correlation in data. So the sort of generative model here is that we're going to have effects due to the models, but like a random intercept, and that would account for this effect. Like, if we can think of these curves as having roughly the same pattern, but it just shifts up and down depending on the resample, that's like a random intercept model. And I didn't pick that because it happened to work out this way. This is really, really typical for these types of data sets. So what I want to do is I want to fit a Bayesian hierarchical generalized linear model. It's a lot of words. And what that means is the R-squared is going to be a function, we're going to say it's, let's say it's normally distributed with some random intercept beta 0 and some systematic effects for the models and some sigma squared. And so what we would do in the Bayesian analysis is we would put prior distributions on these parameters. And it's pretty common to, and that's what makes it a Bayesian model, is we're saying that there's a statistical distribution of these parameters prior to seeing the data. And then what Bayesian analysis does is it blends those prior distributions with the actual data we collected and merges them to some degree together to get what they call the posterior distribution. And I had a bunch of titles for this talk that kind of got rejected because there's a lot you can do with posterior as the title. But what this comes down to is we get like a random intercept model, so we can account for the within correlation problem and then treat it like it's a linear model, right? So we're going to model the R-squared data now. So that works pretty well. So I have this package called Tidy Posterior that does this. And it basically uses stan to fit the model. And there's a lot of flexibility in terms of how you do this. So when I first started thinking about doing this, I thought, well, geez, I have R-squared values. That's probably, those are bounded between 0 and 1. So, I probably shouldn't assume normality about that, right? That's probably not a good idea. But it turns out in many cases, not this particular one, but you're okay using normality. And the idea is like the central limit theorem we think of is we start looking at averages of data points, no matter what their distribution is, right? Central limit theorem tells us that those averages, as the data gets bigger, tend to convert to something that looks more normal. And basically, R-squared, root mean squared error, things like that are almost like averages of our individual data points. So they tend to behave pretty well. So, there are times where you might want to change the length function, or you might want to assume gamma distribution. You can do all that in the package. What I did here was the R-squared values, in some cases, were relatively close to 1. And so what I didn't want to do is have my posterior distribution saying you could have an R-squared of 1 point something. So what I did is I pre-transformed the data on a logit scale. So the logit would basically translate the 0, 1 values to potentially negative infinity and infinity, and then do the data analysis on that. And so that's what the Bayesian analysis is on, is like the logit of the R² values. And then the cool thing is when you get your posterior distributions back, you can just untransform it to get back to the original unit. So it doesn't really cost you anything. And that, in my experience, that is better than using a logit link or something because just convergence is more difficult that way. So here's the result. So what happens is you get these distributions for these models. And you can see these violin plots, which we were having dinner like yesterday or last night. And Hyla's like, I hate violin plots. I'm like, oh, like, good thing he's not here right now. So what you get out of this is you get like these posterior distributions. So you can see the bagged model has a pretty wide variance. And maybe let's say it's the center of that distribution is about like 0.79. So it maybe didn't do so well. But then for Mars and random forest, looks like random forest is doing a little bit better, but just by a little bit maybe. And those distributions are a little bit tighter. The reason for the difference in variation between those distributions is because I put it on the logit scale. So you do a logit normal model, basically when you transform it back, you're not going to get necessarily symmetric data. And it makes sense because for something between 0 and 1, you would think that the variability in that statistic is higher in the middle. Because as you start pushing more and more closer to 0 or 1, those distributions should get compacted to some degree. So it's a fairly realistic, at least to me, it seems like it makes a lot of sense. So what you can do is if you wanted to say, OK, well, let's say I like random forest, you can basically get credible intervals by looking, let's say, percentiles of these distributions. And you can say, oh, my random forest model, I think the true performance is about 89.1%. It could have been as high as like 90.5% if it's like 90% interval, or it could have been, with the 90% probability, it could have been as low as 87.8. Right, so it lets you, what's cool about this is it lets you make comments directly about the thing that you want, instead of like a confidence interval, or even worse, like what a p-value would give you. It's like you have these like convoluted interpretations of the things we're trying to get to. So the thing about it is, I said in the title, practical differences. And so, if I'm comparing Mars and random forest, that's like maybe a 1-point-something% difference in R². Is that a practical difference? Is it real? So what we can do is once we get the posteriors for these things, it's really, really easy to get the posterior of the difference in R². Okay, and so what you can do is now you can think about, well, when I compare models, I can get like a Bayesian estimate of the difference in R² between these models, and then maybe put an interval on that. Okay, so what we can do is we can do some things with the R². Now, there's this idea of like a rope estimate, and so a rope stands for region of practical equivalence. And what these people thought of is, well, let's say I put something, before I start modeling, I say, okay, I'm looking at R² for house prices. What would be like, if I had two models, without seeing the data, if I had two models, how big of an R² difference would I want to see to say that's a real difference, right? And that's really subjective. So you might say 1%, somebody might say 5%. I decided to say 2%. So let's say I had a model that was like, R² was like 0.78, another one that was 0.8. 2% difference is probably practical enough for me to feel like that's a real thing, okay? It depends. She just looked at me like sketchy, like side-eyed me. She was like, I don't know. But it is subjective. But what you can do is once we get the posterior for the difference between these things, you can look at it in terms of, well, is a 2% difference realistic given the results that we have? And a big part of that's the uncertainty that we're collecting. So if we're looking at random forest versus Mars, here's what the posterior difference, or the posterior of the difference in R² between those two models. It is slightly positive because our random forest does a little bit better than Mars. You can see the tails of it maybe are around like, I don't know, point maybe 0.03 or negative 0.03. It's roughly symmetric. If we were looking at statistical significance, like the old school sort of significance, we calculate maybe how much of that distribution, what percentage of that probability distribution is to the right of 0. Right? So that's saying, is there any difference between these models? And you could calculate that probability really easily with the posterior. But what the dotted lines are the region of practical equivalence. And what that means is how much of the posterior distribution is within this plus or minus 2% that I think is like within that 2%, it's not a real difference. And so what people typically do is they calculate the percentage of the posterior that's inside those bounds. So what they would say is, in this particular case, 93.5% of that posterior is within plus or minus 2%. So you would say the probability of practical equivalence between these two models, given sort of like the yardstick of 2%, is really, really high. So based on that sort of measure of what I think a real difference is, you would probably conclude there's nothing different between these two models, right? So you would say that it's not a big enough difference for me to think it's, maybe it's statistically significant, but it's not practically equivalent. And this might be a big deal because if you're thinking about this, Mars is a really, really easy model to put in, let's say, Excel or whatever you want. The prediction equation, that's really nice. Whereas random forest comes with thousands of trees that have maybe hundreds of splits and things like that. So you might have a much faster implementation of your prediction equation that you could probably feel pretty good about it having equal uncertainty or equal performance to this other model. Okay, so that's all it does. Basically the package is called Tidy Posterior, and I did it using results from this other package called RSample that we've written. It also works with Caret, so if you're using Caret, if you've used Caret, there's this function called Resamples that collects all the resampling results and analyzes it. This is like the resamples with like mag wheels. It's like the badass version of resamples. And it basically works the same way, but gives you different analysis results. And that's the end.